Let's talk about NFTs next, non-fungible tokens. That is, tokens that can only exist once, where there's only one coin in existence. The examples of native tokens that we have studied so far are definitely not NFTs, because we could easily mint as many as we wanted of those. Both in the first example, where minting was totally uncontrolled, but also in the second. As long as you are the owner of the specified public key hash, you can mint as many tokens as you like. Now, in order to produce an NFT, maybe the first naive idea would be to actually, in the policy, look at the TX info mint field, which we haven't done so far. All we did look at in the last example was the signatories of the transaction. But if we actually look at the TX info mint field, we could add a condition to the policy that the forged value has an amount of 1. But that wouldn't help us. That would only mean that during one transaction, you can only mint one token. But nobody could stop us from submitting as many of these transactions as we like, and then again mint arbitrarily many tokens. So that won't do. That won't enable us to guarantee that a given token can only exist once. The second option that has been possible since the Mary era, which predated the Alonso era that brought us Plutus, is to use deadlines. So we saw in previous examples, in previous lectures, how time can be incorporated into Plutus script. And we can do the same, of course, in policy scripts. So the idea here would be to have a deadline that only allows minting before the deadline has passed. Then if you want to do an NFT, you mint one coin before the deadline has passed and then allow the deadline to pass. And then it's guaranteed that after the deadline, no new tokens will ever be minted. But in order to check that before the deadline you only minted one, you need something like a blockchain explorer. You must check on the blockchain that only one of these tokens was ever minted before the deadline. You're guaranteed that after the deadline, no new ones can be minted, but in order to make sure that only one was minted before the deadline, you actually have to check with the blockchain explorer. So in that sense, the NFTs that use this Mary era deadline mechanism are not true NFTs in the sense that the currency symbol by itself guarantees that they are NFTs. In order to check that only one exists, you have to look on the blockchain. Now, using Plutus, it's actually possible to mint true NFTs, where if you know the policy script that corresponds to the currency symbol, you can be sure that only one such coin can be in existence without having to resort to something like a blockchain explorer. And if you think about how to do that, you must prevent from there ever being more than one minting transaction for the token in question. So whatever you write in your policy script, it must only result in true for one transaction. And it must be impossible to do the same again in another transaction. And at first, that sounds impossible, because why can't you simply do the same transaction again later, and then validation should again succeed, and it should be possible to mint token again. At least if you do it in the same slot. I mean, we mentioned deadlines before, so of course time plays a role. But why can't you simply at one slot issue the same transaction several times? And the key here is that we need something that's unique. We need something on the Cardano blockchain that we can refer to in our minting policy that is unique, that can only exist in one transaction and never again. And that is a very important trick, something to keep in mind. And the idea is to use UTXOs, because for the reason how UTXO works, UTXOs can only exist once. Every UTXO is unique. You can never have the same UTXO again. A UTXO is there, and at some point it may be consumed as input to a transaction, and there can never ever be the same UTXO again later in the life of the blockchain. Of course, there could be another UTXO that goes to the same address and has the same value and has the same datum, but that will still not be the same UTXO in the sense it will have a different ID. So what is the ID of a UTXO? Well, a UTXO is the output of a transaction. So in order to pinpoint a specific UTXO, you must pinpoint the transaction it came from via its transaction ID, and you must say which output of that transaction it was. The outputs of a transaction are ordered, so by specifying the transaction that produced it and saying which item it was in the list of outputs, you can uniquely identify an UTXO. And transactions are unique. There can never be the same transaction again. And because transaction and index determine the UTXO, this implies that UTXOs are also unique. So now, of course, you can ask, why are transactions unique? And that is a bit subtle, because they wouldn't be unique necessarily if it wasn't for fees. If it wasn't for fees, you could have a transaction that has 0 inputs and only outputs without value. So transactions with no inputs and outputs where each output doesn't have a value. Such a transaction could exist several times. You could have the exact same transaction and it would have the exact same hash and hence the exact same transaction ID. But in a system with fees like Cardano, you can't have such a transaction because you always need an input that provides the fees to pay the transaction fees for the transaction. And as soon as you have an input, that input must come from somewhere. It must come from a previous UTXO. So basically, by a simple induction argument, you see that as soon as you have fees, transactions can never be repeated. You can never have two identical transactions in the sense that they have the same transaction ID, because they must spend fees, and these fees, because double spending is impossible, must be different UTXOs for different transactions, and the inputs are incorporated into the transaction hash. So if you have two transactions with different inputs, those two transactions also will have different transaction IDs. So that means that every transaction in the history of the blockchain is unique, has a unique ID, and that implies that also every UTXO in the blockchain has a different ID, a different combination of transaction ID and index. And this is a very important fact, and that is a fact that we can use in order to create true NFTs. So the idea here is to name a specific UTXO as parameter to our minting policy. And then in the policy, check that the transaction that does the minting consumes this specific UTXO. And because of what we just said, once a UTXO has been consumed in this transaction, it can never exist again. So there can't be another transaction that consumes the same UTXO. And this strategy guarantees that with a minting policy like that, there can only ever be one transaction that consumes this UTXO. And that is what we want to achieve in order to guarantee that we have a true NFT that can only be minted once. In order to demonstrate the idea, I created a module NFT. And in the make policy function, I now have two parameters, one of type txoutref, one of type token name. So txoutref, as the name suggests, references txout, so transaction output, UTXO, and token name will be the token name of the NFT. There would be various other choices. For example, I could turn those two pieces into one parameter. But I also wanted to demonstrate how to have scripts with more than one parameter. So how does it work? So oref is the reference to the output we want to consume in this transaction to make sure that this can only happen once in one transaction. and TN is the token name. Again, we don't use the redeemer, and the context. So we have to check two things: that the UTXO specified by OREF is indeed consumed. So that's the first condition here, that I delegate to has UTXO, the helper function. And the second condition is that we indeed only mint the token once, exactly once. So let's look at the helper functions. First, just the txinfo, because I need that in both helper functions, in both checks. Now the has UTXO. If we look at the documentation for txinfo again, this is now the first time that we don't just use global field that applies to the transaction as a whole, but have to actually look at the inputs, at individual inputs, because we have to make sure that this transaction, this minting transaction, indeed consumes the specified UTXO. So we will use this txinfo inputs field, which runs a list of type txininfo, and if we check this, we see that txininfo has two fields, and one is called txininfo_outref and is indeed of the right type of txoutref. So as you recall, an input consumes an output from a previous transaction, and this specifies which output. So going back to the code, any is a standard Haskell function that checks whether any, that is at least one element of a list, satisfies a condition. So for example, I can check any even 235. That will be true because 2 is even. But if I change that into a 1, it will be false. Okay, so we check that any of these, and this we just looked at, so that is an input of the transaction. So I is now the input, and we use this function we looked at in the documentation just now. So this is now the output reference that this input I consumes, and we check whether this equals the given UTXO. So this line checks whether there's any input that consumes this output. So that's the first condition. And the second condition, we actually look at this txinfo mint field that tells us what is minted or burned in this transaction. And we use the flatten value function that we discussed earlier. And we expect that only this one NFT, so this one coin, is minted. So if we get a list that contains not exactly one triple, we know something is wrong anyway, and we can report false. So we expect this one triple. And now we have to check that the token name of the triple that is minted or burned is actually the expected token name, the one coming from the second parameter to the contract. And we check that the amount minted is 1, because NFT means we only want to mint exactly one coin. So that completes this function, the make policy function. Now we need to compile it to a policy. So given the two parameters, the txoutref and the token name, we must compute the minting policy by compiling this function. This is more or less as before. The only difference is that now for the first time we have something with two parameters. But that just means we have to apply code twice. So giving this, we have a function with two parameters. We apply the first argument here, the lifted reference to the UTXO. So we are left with a function with one parameter, the token name, and then we apply the lifted token name, and we are left with something of the right type redeemer to script context to bool. So once we have our policy, we can compute the currency symbol also as before. So given the two parameters, we use the policy function we just defined and then get the policy and then can apply a script currency symbol to it. So that concludes the on-chain part. The policy itself. Now in order to try it out, let's write an off-chain code contract that can actually mint an NFT. So how do we do that? What parameters do we need? Well, we certainly need the token name, but we also need the TX outref, the UTXO we want to consume. And of course, we could specify that as another parameter, but then it would be a bit inconvenient to use because a user would somehow have to look up UTXO, a TX outref that is in his own wallet. So it's easier to instead give the user's address, and then we can use the contract monad functionality from the contract monad to find a UTXO that we can use as this parameter for our policy. So we define our NFT parameters as record type with these two fields, token and address. And then we define our schema as just having one endpoint that we call mint with these parameters. And now we can define our contract monad code. So it takes these parameters. Then we use UTXO's add that takes an address for which we take the second field from our parameter, and it will return all the UTXOs at that address, which is a map from TX outrefs to actually the outputs. So it's a normal Haskell map, so it has this map.keys functionality, which gives us the keys, which are the TX outrefs, and we are interested in those. So if there is none, so if there are no TX outrefs at this address, then we log an error. And if there is at least one, we just take the first one because it doesn't really matter which we take. Then we just for convenience, we find the token name, then the value we want to mint. So we use this value singleton function again. So recall that takes the currency symbol and the token name. Currency symbol we can compute with our cur symbol function now that we have the TX outref that we want to use and the token name. The token name is the given token name, and the amount is 1. As lookups, as before, we must specify the policy, the full policy. It must be included in the transaction with this constraints.minting policy. And we also need to provide the UTXOs for the transaction to be able to be constructed. We wouldn't need the full UTXO set because we only need this one, the TX outref we specified and the corresponding output. But it doesn't matter if what we specify here is too big. The one that's needed must just be contained in this dictionary. So to make our life simple, we can just use the full UTXOs sitting at that address. And constraints for the transaction. So we can use the must mint value again with the value we computed earlier. And there's another constraint, must spend pub key output. And now we insist that this transaction we are constructing spends this oref, the TX outref that we found. Then we can submit, wait for confirmation, log a message. So that's that. And we can define endpoints again as before. So that's exactly the same. But we don't really need that, except now in the emulator trace, we can exercise our code. So we again pick some arbitrary token name ABC, and we try it for 2 wallets, 1 and 2. We start the contract for both these wallets, and then we call the mint endpoint for the first wallet with the following parameters. So as token name, we use this predefined token name ABC, and the address, now we need this wallet address, and there's a function called mock wallet address that takes a wallet. So if this wallet is a real proper wallet, this would result in an error, but if it's a mock wallet and these known wallets are mock wallets, then it will actually give us an address for this wallet. and simultaneously in the same slot we also call the mint endpoint on wallet 2. So same token name but a different wallet address. And we just wait for one slot. In the REPL we load the module and then we can run our emulator trace. And we see we indeed have two wallets that end up with one token each, token name ABC, but we note that the currency symbol is different. So it's not as if we somehow managed to end up with 2 coins of one NFT, which would mean it wasn't an NFT after all. These are 2 different proper NFTs. So they have different currency symbols. And why? Because one of their parameters was the UTXO that was consumed. And of course there were different UTXOs in the one wallet and in the other wallet. The currency symbol is completely different. The token name of course is the same. We could have picked a different one, but we can also pick the same one. So just as a recap, the idea with NFTs, the idea to enforce that only one transaction can mint is to use a UTXO as input, to insist in the policy, in the minting policy, that the minting transaction uses a specific UTXO as input. And because UTXOs can never exist again, once they have been consumed, the same UTXO will never exist again. This will guarantee that such a transaction can only happen once. And if in addition we enforce that in this transaction that can only happen once, a value of exactly 1 coin is minted, then we get a policy that guarantees that we have a proper NFT, where there's only 1 coin in existence.